So we have an overall reaction, which is the ones that we've been dealing with up until this point are just overall reactions. But now we're looking at how to break these down into individual elementary steps. We're going to talk about the step that's the slowest compared to the fastest. And then we're going to be able to recognize intermediates in the elementary steps. So if we go back down, let me see if my undo powers will still work. Nice. Okay. So I'm going to clear up a little bit of the clutter. Now, if I were to provide the information, and often this is provided to you, that the first step is very slow compared to the second step. So once NO3 forms, once nitrate forms, well, it's not nitrate, nitrogen trioxide. Once nitrogen trioxide forms, it reacts very fast with carbon monoxide. And so essentially, the rate of the reaction depends on the weakest step or the slowest step. It's kind of like if you're running a 4-person race and everyone has to cross the finish line, your time is based on the slowest runner. I don't know if they still kind of do that in track. Who's the track person in here? Does that ever happen? It's like the baton thing, you're all running independently, but if you run on a team and your time is based off the slowest person, it's kind of the same idea. The slow step has NO2 and NO2. If I were to combine that, that'd be 2 NO2 because of the coefficients, right? Thanks, buddy. Obviously, I didn't do track. I've watched maybe 1 or 2 track meets, but so that's not a thing. Hypothetically, it's a thing, but in chemistry, it's a thing. Now, ignore the fact that you're adding those together to get a coefficient. If I were to write the rate law based off just the slowest step, the rate law of this step would be K NO2 times NO2, because those are the reactants and we multiply the reactants. But because it's the same thing, I can just transfer that to NO2 squared. So if we do a rate law based on the slow step, and each of these represents one molecule colliding with another molecule, this order, second order, represents, in a reaction mechanism, we now get a stronger definition of second order. This means that 2 NO2 molecules collide. So the rate of this reaction is based on how fast and efficiently 2 NO2 molecules collide with each other. And with reaction mechanism, it's kind of nice because the order of the reaction, whether it's 0, first, second order, the order of the reaction is now based off just reading the reaction instead of doing all this data analysis and crunching numbers. The way we get a rate law can be based off just the slowest elementary step. So I'm going to write that last thing. If we go back up to, one second, the rate determining step, the slow elementary step by which the okay, freaking out. By which the rate law is determined. So we look at the slow step and we write a rate law based on the particle that's colliding, and the order has to do with how many particles show up in that, on that reactant side of the rate of the reaction. So in this case, we have 2 NO2s, so there's 2 molecules, and so it's second order with respect to NO2. This is where the coefficients matter. And the coefficients essentially equal the order of the reaction. When you do mechanisms, you don't have to crunch numbers. You just look at what particles show up in the reactants of the elementary step. So to add on to your notes, rate law is written as the reactants of slowest elementary step each reactant counts as its order. There's probably a better way to say that second thing. Let me just show you an example. So on your, there's sample 2 on the one that's printed out or typed out for you. There's an overall reaction here. And then it's broken down into 2 possible mechanisms. You have the first potential mechanism, which is a 2-step mechanism, and a second mechanism, which is another 2-step mechanism. If we were to write the rate law based off of each of these slow steps, if we look at the rate law from the slow step, the first mechanism would be based off of this slow step here. And so we look at the reactants. There's just one reactant. And so we give that a name. When there's only one reactant, we say it's unimolecular. And the rate law for that step is just based off of that one reactant in the slow step. So we're going to take that and just say NO2. There's one of them, so it's first order. Unimolecular, first order. Just the reactants of the slow step. It's a much easier way to write the rate law than crunching all those numbers. But you have to have a proposed mechanism. The proposed mechanism for the rate law for the second one is again based off the slow step, because the reaction's going, the slowest step kind of hinders the reaction, and the fast steps just happen so much faster than the slow step. So if we understand how fast, or we understand the rate of the slow step, that's essentially the speed of the reaction. So in this case, we have 2 particles. You see the coefficient of 2 here. We have 2 particles. It looks like one reactant, but there's a coefficient of 2. So that's technically NO2 plus NO2. So the rate law would be, we just kind of did this one, NO2 and NO2, which is 2 NO2. So we're just going to combine those and to say the rate law is K NO2 squared. So this is where the coefficient becomes the exponent. So there's some questions that ask, what is the rate of the reaction given this mechanism? And it seems like it should be tricky, but it is not. You just need to know what to look for. You look for the slow step of this mechanism, whether it's 2 steps, 3 steps, 5 steps. You look for this one that says slow, and that'll be given the vast majority of the time. We'll look at some ways to figure that out if it's not given. You find the slow step and you just write the reactants down in the rate law. Make sure K is there. K is still there. It's this arbitrary value that you can figure out if you need to. Rate equals K times the reactants, and the coefficients become the order, and you're done. That's the rate law. Much easier than dealing with an overall reaction. If you break it down into mechanisms, use the slow step. So that's how you write the rate law from a mechanism. Let's try it out. I'm going to space mine so you're only looking at one at a time. Oh, I turned on comments, that's why. Okay. So let's look at practice 1, and I'll do one and then I'll have you try a couple, or we'll do one together. Yes, that's a very good question. So far, all of the examples have had the slow step as the first step. Is this common or just a coincidence? There is a reason for that. If it is not, if the slow step is not the first step, we got to do something different. So right now, the slow steps are the first steps. If you notice step 1, this one doesn't mention which one's slow, but slow. There's a thing you got to do with equilibrium and some little bit of substitution if it's not, if the slow step's not the first step, and that's something for later. Very good observation. And that is explicitly mentioned in the text. It's mentioned in the supporting videos that I posted. So we'll get there. I believe I attached those videos. I'll check. Anyway, practice 1. So couple goals. First, rate law expression. We're going to write a rate law. 2, what are the intermediates? Identify ID the intermediates. So the overall reaction is given. So when you cancel, when you do cross canceling, it should add up to equal the overall reaction. This is very similar to one that I showed you as a demo. This was the elephant toothpaste reaction. My catalyst was different. I didn't use bromine, I used iodine, but essentially does the same thing or similar. So when I look at the rate law expression, we have the slow step, and I have everything in the slow step right there. And that is a lot, by the way. Usually when you break it down to mechanisms, it's a little bit more broken down than that. So I'm just going to take my reactants in the slow step and say the rate of the overall reaction is based off of Br squared because of the coefficient, H plus squared, and H2O2. On the side, I'm just going to say this is not likely. But this is hypothetical. This is if could the reaction proceed like this? What would the rate law expression be? Now we could test it. If this is a proposed rate law, if this mechanism work, this could be the rate law. Let's test it and determine the order of the reaction with respect to all the ingredients. Then that's where you go back to the lab and measure time and figure out changes in concentrations and figure out the order to prove this proposed mechanism. But right now we just get to theory craft and write them down. So let's see what canceled. Br minus cancels with Br minus. There's 2 of them. H plus cancels with H plus. There's 2 of them. Notice how those do not show up in the overall reaction. They cancel out. And another one that cancels out is Br2. Everything that I've boxed cancels out. The intermediate is just Br2. There's a specific thing to the intermediate. It must be formed, must be a product first. It must be made in an early reaction and then consumed in a later reaction. It must be produced, then consumed. So what are these other ones? What are the red ones? Br minus and H plus. They're ingredients. They're actually reactants in the first step. These have to be supplied. They're ingredients. They wouldn't be there unless you brought the chemicals to the reaction. And they're released later on. They're products later on. So they're reusable. You bring them in, they're used up in the first reaction, and they're reproduced in the second reaction. These are catalysts. A little bit about catalysts is they're reusable. They must be supplied, but they are reusable. Reusable or recreated. They're products at end of reaction. So they have to be ingredients first. Catalysts need to be supplied. You have to include them, and then they're reproduced later on the reaction. All catalysts do is create the mechanism for which the intermediates can form. Br2 would not be an intermediate if you did not bring the catalyst bromide, Br minus. If bromide was never introduced, Br2 wouldn't be an intermediate. So the catalyst is adjusting the mechanism and creating the efficiency, the speed of the reaction is derived by this catalyst creating the Br2 intermediate. So we have intermediates, which there's only one of them, even though a lot of stuff canceled out. Br2 is just an intermediate, and then we just mentioned the catalyst. So let's go back to our definition, and I'll clarify the catalyst definition. Let's scroll back up. Hopefully this format isn't too obnoxious. A catalyst, used as an ingredient to change reaction mechanism. Produced in a later step, which means they're reusable. Again, these do not show up in an overall reaction. So intermediates and catalysts, you're not going to see an overall reaction, but they're there. They're doing work. They cancel, essentially. When you're finding an overall reaction, intermediates and catalysts will cancel out. The rate law equation is still that rate equals K, A, B, etc., where the rate is based on the slow elementary step and proven by data analysis. I'm going to zoom in a little bit. If you're on your phone and you can't see this, then hopefully that's okay. I'm just going to define the molecularity stuff really quick and try not to be too wordy, and then we'll move on. I'll get you to practice because we're already at 2:25. As you can tell, there's a lot of verbiage here, but when you get past it, it's like learning. I don't know why I think of this, but it's like learning a tricky board game. There's some board games out there that's a little tricky to learn, but once you learn it, it's actually not that hard. You just get some practice in. The one that I played a lot was Settlers of Catan. Try explaining that game to someone and get them understanding it the first time. And then once they try it and practice, it's just like, oh, this isn't that hard. Anyone knows that game. That's a fun game. But molecularity. So I'm going to abbreviate rate determining step as RDS. Rate determining step, RDS. Molecularity is the number of particles in rate determining step. Someone has experience with that game. You know, so there's a game that, a board game that my friends and I got into. It's a dumb one, but maybe I'll show you the box when we're all done with this. Gloomhaven. No, thank you. My buddy played that. Gloomhaven. Man, that is a complex game. Well, it's some version of Dungeons and Dragons, but anyway, I'm not going to get that. Anyway, unimolecular. Rate determining step has, sweet, my font is changing. Rate determining step has only one particle. Bimolecular. Rate determining step has two particles. They can be this. You can paraphrase this. Be the same or different substances. Termolecular rate determining step has, you guessed it, three particles. Same idea. They can be the same or different substances. They just need to add up to three. Coefficients add up to three. Beyond that, unlikely. And we just saw an example, there's five. The coefficients add up to five. That's not a great mechanism. These mechanisms are considering collision theory. These particles have to collide in the perfect orientation with enough energy for the products to form. And if once you have three, a termolecular, that means these three particles have to collide in the right orientation, the right way with enough energy. It gets pretty low probabilistic, yes. And so if you're looking at a reaction and you're just trying to figure out which step could be the slowest, and you don't have much information to go off, you just have a mechanism, usually the higher molecularity is going to be the slower step because it's less likely for all these particles to collide in the perfect orientation. Unimolecular steps tend to be pretty fast. Termolecular steps tend to be pretty slow. But the higher the molecularity, the less likely it is to that particular reaction to be successful. This one, practice 2, is actually the one that I did in the demonstration because I'm using iodine, which is a catalyst. Iodine was the catalyst I used for the elephant toothpaste, and you get this cool little graph here. For practice 2, just identify the intermediate. What is the intermediate? Got it. Perfect. IO. In binary, that probably means something. IO is the intermediate. It is produced in the first step, and it is a reaction in the second step. That is an intermediate. Is there a catalyst in the reaction? I minus. I minus is a catalyst. It is supplied in the first reaction and released in the later step, one of the later steps. So this is a catalyst. So let's look at the graph. When you have this is an uncatalyzed reaction versus a catalyzed reaction. The uncatalyzed reaction is really slow. This is hydrogen peroxide in a cup decomposing. It's not actively bubbling. It just happens pretty slow over time. If you put hydrogen peroxide in a cup and leave it out on your desk, it'll eventually turn into water. The oxygen gas escapes. But catalyst makes it happen much faster. So there we go. And this is an image. This blue step is the adjusted energy diagram for a catalyzed. Notice the reactants and the products are the same. The only thing a catalyst does is affect the pathway. It affects the kinetics, the in-between part. The catalyst doesn't change the overall reaction, it just changes the mechanism. All right, what else? I'm just kind of skimming these some examples. You can look at this. Two substances, this is bimolecular. One substance is unimolecular. And then two substances is bimolecular. Just some examples. Let's take a quick look at this last one so we get some context. These are would be all elementary steps, by the way, of their own mechanism. This doesn't necessarily add up to a different mechanism. Let's do this. And I want to move on to another set. Okay. The reaction, look at practice 4. The reaction equation for the thing below shows, here's the overall reaction in bold. Experimentally determined rate law. Which of the following proposed mechanisms is consistent with the observed rate law? Is mechanism A or mechanism B the best choice to match an experimentally determined rate law? A or B? You can just mention in chat. And this is, again, this is kind of what I said earlier. It's not supposed to, this particular skill that we're learning is not meant to be tricky. You just got to know what to look for. And it almost seems like, is that it? Based on all the question types that we've been doing, all the steps that you do in these kind of questions. Now we get to this stuff and you're just saying, okay, all I have to do is look for this one that's the slowest and it tells me it. And I just look at the reactants and that goes in the rate law. Yes. Appreciate the simplicity for this particular task because it can get more complicated. So that's it. That's all you got to look for. The slow step, and thank you in chat. I noticed you guys saying the right mechanism. These are some sample questions you might get on the AP test. Gives you a rate law. You have 4 of these, and you just choose the one that correctly has the reactants and the slow step as in the rate law. So where do we go from here? There's some details with these graphs that I want to get into on Monday. So we do have another day of practice and looking at some variety of examples. And I have some worksheets that we're going to be going through on Monday. And Monday, I want to get you back in groups where you're looking through some examples together and identifying intermediates and catalysts, and then looking at some more examples of these multi-step energy diagrams, which gets us to some fun little interactions that we'll be able to address on Monday. So Monday is going to include some classwork, less me talking, more you just trying it out, which I think you'll appreciate. Where do those YouTube clips go? I might have to add them again. Did I just, oh, there it is, saved announcements. Ah, okay. Additional videos for reaction mechanisms. So this goes over what we did today. It also goes over some of these videos as far as mechanisms go, what you can find in the textbook, but here's another resource. I would encourage you watching these. These are just 5-6 minute clips. This is, again, another preview of where we're going. Great animations and visuals. And these are the two YouTube people that I refer to or basically link the most when it comes to chemistry and AP chemistry. So do some investigations, do a little bit of background work, watch some of the videos, read some of the text, get an idea, a more complete idea than what I can blabber about in 1 hour. Because on Monday, we're going to be doing more. And it goes really quick. And I want to finish mechanisms on Monday because we need to move on. So here's your assignment for over the weekend. In addition to all the independent videos I'm asking you to watch and kind of studying that I'm asking you to do on the side, I tried to keep this short. So we looked over the notes. There is some practice. This is something that the practice problems will attack on Monday. So don't worry about those practice problems. If you want to get a preview and kind of go through this, this is some additional practice. Here's our book work. So I did 5 questions. Yes, there's some ABCs, but there's 5 questions. So this is out of the Zoomed book, same chapter. So you can check the answers to the odds, which are all of them except 64. Write rate laws for the following elementary steps. So if this is an elementary step, what would a rate law look like? And you're going to do that 4 times for different reactions. Here's an entire mechanism. What's the rate law? What's the balanced equation? What are the intermediates? Pretty much exactly what we just did. So just practice this. By Monday, when you come to class on Monday, we're going to finish mechanisms and tie it all together between the first half with the rate law calculations that we did that was focused on the lab and the new stuff with reaction mechanisms. And we'll look at some more challenging situations and variants. Ian brought up, what happens if the first step is not the slow step? What if a later step is the slow step? We have a new way to adjust for that we'll go over on Monday. Other than that, I'm going to give you some time. If you want to glance at the homework, I'm going to leave it up on screen. Look at some of these questions. If you have any concerns about, based on what we did today, let me know. I did record this. So